2.
Yes, sir. To the 1.
So when
Oh, good. Thank you. Never mind. 2 to the 1 bigger than 1. I've seen this proof also where it's not strictly greater than n, but greater than or equal to n, right? A little bit easier for us to prove. Suddenly I was thinking, ooh, we might have a problem seeing that I can't transcribe all of these. Right, so we have 2 to the 1 bigger than 1. Everyone agrees that's a true statement. So our inductive hypothesis would say what? 2 to the k must be greater than k. So we're assuming and what is it we're trying to show? So if we can show that, we're going to be good.
And maybe 2 to the k is strictly greater than k.
Didn't I just copy that what someone said? Thank you. All right, 2 to the k greater than k, right? We've got all the k's. All right, 2 to the k plus 1 bigger than k plus 1.
We need to keep this in mind that k is greater than equal to 1. So
Yeah, because remember what we're talking about here, n must be 1 or 2 or 3 or 4, right? A natural number here. That's always going to be the setup here. So sometimes I have to be careful not to get lazy on that idea. So, any ideas? Right, John? We'll stay up here this time. Thank you.
No, that's fine.
So we're going to take the left-hand side. This one might be a little funky. What's that equal to? Notice what we did with the 4 to the k plus 1 power up there. That's a pretty handy trick, quite often, to think in those terms, right? So really, we have this is 2 times 2 to the k. So what do we know about 2 times 2 to the k?
greater than 2k.
Must be, right, so, right, always have to come back to our, right, inductive hypothesis. We know that 2 to the k has to be bigger, or we're assuming, we don't know, we're assuming that 2 to the k must be bigger than k. So what does that mean here? That's some cheap chalk. 2 times what? K. Right. Far so good. Any ideas?
2 times k is greater than k plus 1.
Why?
You can write that k plus k.
That's, yeah, k plus k.
Well, let's, boy oh boy, my format is getting pretty gnarly here,
And that's great.
but, right? 2k is, think about it, it's just a k plus a k. And what do we know, Josh? What do we know about our value of k?
It's less than
Oh, greater than
It's bigger than or equal to 1. So what does that mean over here? If k is bigger than or equal to 1,
that's greater than.
k plus k must be bigger than or equal to
2.
K plus 1.
Knew that was going to come back. So what have we shown? Strictly bigger than k plus 1.
Thanks.
Is there any flaw there? So notice that we're using some sort of a transitive property of inequalities, right? That must be what we're doing here. Come on, math teachers, help me out. Transitivity of inequalities, yes?
Good.
Right, A is bigger than B, B is bigger than C, therefore A is bigger than C type of idea.
I missed that.
Just get that spinner. All right, we got 2 more to go. Then I'll cut you loose. You see that? So with f of x, we'll get to our calculus kind of examples. I'm not sure I want to bother writing for the next one, but we'll use it. So here, what I failed to write down, all right, this is only going to work. So for those of you who've done your 251, right, you know the power rule. F of x is x to the n, the derivative is going to be nx to the n minus 1. And as it turns out, you can use that when?
N is any.
Yeah, whenever you please, pretty much. Right, I mean, I can give you f of x equals x to the, 6.139. You could drop the 6319 and move your power down to 5319, right? I mean, you apply the power rule pretty freely whenever we have a power function. If we're going to talk about this using induction, of course, we're only going to talk about natural number powers, right? So x to the 1, x squared, x to the 3rd, and so on and so forth. So we should be able to prove that this works for any natural number using induction. Now, in order to do so, we got to remember one little thing. Well, I suppose we got to remember 2 things. If n equals 1, what's f of x? No,
X.
it's
X.
x to the 1, right? So this x. Good. So how do we find f prime without using the power rule? Because that's what we're trying to do.
Quotient using a difference quotient?
Yeah, good old-fashioned limit definition. So let's figure out f prime of x. By definition would be the limit as h approaches 0 of how does the derivative work? Is that a derivative, John? You teach a lot of the calculus, right?
I missed that day too.
Missed that day too. So of course this is x plus h minus x over h, which is of course 1. Right? So, I mean, as far as difference quotient examples are concerned, this one works out pretty nicely. Thank goodness. We've got our base case. We can't use the power rule to get it. Sir?
Would it be legal just to say that the slope is always 1? Or should you do it more formally like that?
I guess for this one you can.
For our purposes, John, let's refer back to the original overhead which said an introduction to, right? I mean, again, I think the question is, right, how comfortable are we with some basic derivatives, knowing that at some point in time we proved this particular right derivative using the definition, right? But, to dot our I's and cross our T's, I'll just, I know you skipped that day. Oops. What do we do with our inductive hypothesis? What are we assuming? That n must be equal to k. So we will assume